Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is the continuation of two-port networks and transmission lines, Part 2. Recall in Part 1, we talked about lossless lines. And for you to follow proper in this Part 2, you are expected to have listened to Part 1. Now, we talk about standing waves in transmission lines. If a transmission line has an infinite length or is terminated in its characteristic impedance, all the power applied to the line at one end will be absorbed by the load at the other end. This type of line terminated in its characteristic impedance is called a non-resonant or flat line. The reason is that the voltage and current in such a line are constant throughout its length. If the line is assumed lossless or are reduced exponentially if the line has some losses. If a finite piece of line is terminated in an impedance not equal to its characteristic impedance, some of the applied power will be absorbed by the termination, while the remaining power will be reflected back to the generator. If this line is terminated in a short circuit, no power will be dissipated in such a circuit, and all of it will be reflected back to the generator. For a lossless line, if a wave is sent out at the input and the source quickly removed, an open circuit will be created at the sending end. The power in the line will shunt back and forth and never diminishes because the line is lossless. The line is then called a resonant line because of its similarity to LC resonant circuit, in which the power shunts between the electric and the magnetic field. If the load impedance ZL has value between 0 and Z0 or between Z0 and infinity, oscillation still takes place, but this time decreases more rapidly with time as the load impedance approaches the value of the characteristic impedance Z0. If the load impedance is equal to the characteristic impedance, the load absorbs all the power and none is reflected, and the current and the voltage waves are represented or are present as traveling waves only from the generator to the load. If the load impedance is not equal to the characteristic impedance, some power is absorbed and the rest is reflected. Therefore, we have one set of waves, V and I, traveling towards the load, and the reflected set traveling back to the generator. These two sets of traveling waves going in opposite directions set up an interference pattern known as the standing waves, as shown in Fig 3. It can be seen that stationary voltage and current minima and maxima have appeared. The voltage maximas as well as the current maximas are separated by half the wavelength of the signal. Note that the voltage nodes and current antinodes occur at the same points along the line as do current nodes and voltage antinodes. If we consider only the forward traveling wave and current represented by the thick line in Fig 3, then at the load, the voltage will be 0 and the current will be maximum because the load is short-circuited. The reflection that takes place at the short circuit affects both voltage and current. The current now starts traveling back to the generator unchanged in phase, but the voltage is reflected with a 180-degree phase reversal. Thus, at a point exactly a quarter wavelength from the load, the current is permanently zero. This is because the forward and reflected current waves are exactly 180 degrees out of phase. At a half wavelength distance from the load is a point at which there will be a voltage zero and a current maximum. This arises because the forward and reverse current waves are now in phase. Simultaneously, the voltage waves will cancel because the 180 degrees phase reversal on reflection must be added to the extra distance the reflected wave has to travel. This condition is permanent for any given load, and such waves are termed standing waves. Much the same conditions apply if the load is an open circuit, except that the first current minimum and voltage maximum is now at the load instead of a quarter wavelength away from it. Now, this leads us to an important term in considering transmission lines, known as the standing wave ratio. The ratio of the maximum current or voltage to the minimum current or voltage along a transmission line is called the standing wave ratio. This is a measure of the mismatch between the load and the line and is the first and most important quantity calculated for a particular load. The standing wave ratio is equal to unity when the load is perfectly matched. When the line is terminated in a purely resistive load, the standing wave ratio is given by Z0 over RL or RL over Z0, depending on which one is larger. Note, the higher the standing wave ratio, the greater the mismatch between the line and the load, or between the generator and the line. In practical lines, power loss increases with high standing wave ratio, and so also is noise. A low value of standing wave ratio is always necessary, except when the transmission line is being used as a pure reactance or as a tuned circuit. It is always usual to normalize an impedance with respect to the line to which it is connected. This is normally obtained by dividing the impedance by the characteristic impedance of the line as shown in equation 8. This is very useful because the behavior of the line depends not only on the absolute value of the load impedance, but also on its value relative to Z0. This can be seen from equation 7. For instance, the standing wave ratio will be 2, regardless of whether Z0 is equal to 25 ohms and RL is 50 ohms, or Z0 is 500 ohms and RL is 250 ohms. This helps to plot transmission line charts, which are used to obtain universal response curves for tuned circuits and radio frequency coupled amplifiers. If a pure resistance is connected to a transmission line such that the load resistance is not equal to the characteristic impedance, the voltage and current will vary along the line as shown in Fig 3, and so will the resistance or impedance. However, conditions do repeat every half wavelength. Hence, the impedance at point P will be equal to that of the load if P is a half wavelength away from the load and the line is lossless. That brings up another important terms, quarter and half wavelength lines. From what we have seen, sections of transmission lines that are exactly a quarter wavelength and or a half wavelength long have important impedance transformation properties and are of great application at radio frequencies. If a load of impedance ZL is connected to a transmission line of length L and having Z0 as its characteristic impedance, and L is exactly a quarter wavelength or an odd number of quarter wavelengths, and the line is also lossless, the impedance seen when looking towards the load is given as ZL equals Z0 squared over ZL. This equation, though very complex, represents a very important relationship. At point P, that is voltage antinode and current node, the line impedance is low, and at point Q, the reverse is the case. In order to change the impedance at P, it would be necessary to change the standing wave ratio of the line. If the standing wave ratio is increased, the voltage minimum at P will be lower, and so will be the impedance at P. In the same way, the size of the voltage maximum at Q will be increased, and so will be the impedance at Q. Therefore, an increase in ZQ is accompanied by a decrease in ZP if P and Q are quarter wavelength apart. This means that the impedance at P is inversely proportional to the impedance at Q. If a load is connected to a transmission line and matching is required, a quarter wave transformer may be used if ZL is purely resistive. If the load impedance is complex, one way of matching the load to the line is to tune out the reactance with an inductor or a capacitor and then match with a quarter wave transformer. At high frequencies, short-circuited transmission lines are more often used than lumped components to achieve matching. A transmission line used to achieve this is called a stub. The various properties of these transmission lines are represented graphically on a large number of charts. However, the most widely used one is the Smith chart, which gives the impedance relationship that exists along a lossless line for different load conditions. The Smith chart consists of two sets of circles or arc of circles which are so arranged that various important quantities connected with mismatched transmission lines may be plotted and evaluated easily. The complete circles, whose centers lie on the only straight line on the chart, correspond to various values of normalized resistances given as R equals to big R over Z0 along the line. The straight line is actually an arc of a circle with its center at infinity. The arcs of circles to either side of the straight line similarly correspond to various values of normalized line reactance. The various circles and coordinates have been chosen so that conditions on a given line with a given load, that is constant standing wave ratio, corresponds to a circle drawn on the chart with its center at the center of the chart. The greatest advantage of Smith chart is that movement along a transmission line under almost all imaginable circumstances corresponds to movement along a correctly drawn constant standing wave ratio circle. Other applications of Smith chart include admittance calculations, impedance calculations, and calculations of the length of a short-circuited piece of transmission line to give a required capacitive or inductive. Thank you for listening. Like, share, and subscribe so that you get more models at your doorstep.